how AI actually understands us, taking you from the basics of text processing to the revolutionary architecture behind ChatGPT. For decades, we tried to teach machines to understand language by breaking it into numbers. We used techniques like word2vec to give words meaning based on their neighbors, ensuring that king and queen sat near each other in a mathematical space. But there was a massive flaw. These models were context blind. You were talking about a river or a robbery. To fix this, we developed recurrent neural networks, RNNs. These models processed text like a human reads a book, one word at a time from left to right. As they read, they kept a hidden state, sort of mental note of what they'd seen so far. But as sentences grew longer, the AI would forget the beginning. This is known as the vanishing gradient problem. Even improvements like LSTMs, which added a specific cell state to act as long-term memory, struggled with the sheer scale of the internet's data. The breakthrough came in 2017 with a paper famously titled "Attention is All You Need." This introduced the transformer. Instead of reading sequentially, the transformer uses self-attention. It looks at every word in a sentence simultaneously. When it sees the word bank, it immediately checks every other word in the sentence for clues. If it sees water, it adjusts the mathematical representation of bank to mean a riverbed. The architecture is split into two halves, the encoder and the decoder. The encoder's job is to create a rich map of the input text, understanding the relationships between every token. The decoder then takes that map and starts generating a response one word at a time, and it uses masked attention to ensure it only looks at what it has already written, and cross attention to keep referring back to the original input map by adding multi-head attention, essentially giving the AI multiple sets of eyes to look for different types of relationships. And positional encodings to keep track of word order. The transformer became the engine for the LLM revolution we see today. Optimization. While the original transformer was groundbreaking, researchers soon realized it could be made more efficient. One key evolution is how the model understands the order of words. While early models added fixed mathematical curves to word embeddings, modern models like Llama use rotary positional embeddings, ROPE. This technique rotates the mathematical vectors of words in space based on their position, allowing the AI to understand the relative distance between words more naturally. We also saw improvements in how models stabilize their learning, moving from post-layer normalization to pre-layer normalization, a simple shift in where we clean up the data that dramatically speeds up training. The second chapter introduces the encoder-only family headline by BERT. Unlike the full transformer, which translates between languages, BERT focuses entirely on understanding. It is bidirectional, meaning it looks at the words both to the left and the right of every single token simultaneously. To train BERT, researchers used a clever game called masked language modeling, where they hide certain words in a sentence and force the AI to guess them using the surrounding context. However, BERT was often too large for real-time use, which uses a process called knowledge distillation. Think of it like a teacher model, BERT, showing a student model, distill BERT, exactly how it thinks. By learning the teacher's probability distributions instead of just the final answers, the smaller student model can retain 97% of the performance while being 40% smaller and 60% faster. We also saw Roberta, which proved that by simply training the model on more data for a longer time and removing unnecessary tasks like next sentence prediction, we could push the boundaries of accuracy even further. Today, while large language models, LLMs, often use only the decoder side to generate text, these encoder-only models remain the gold standard for classifying sentiments, extracting information, and powering the search engines we use every day. Mixture of experts, MOE. Think of an LLM like a room filled with experts, a mathematician, a historian, and a chemist. In a traditional dense model, every single expert is involved in every single question, which is incredibly slow and expensive. In a sparse MOE model, a router or gate identifies which expert is best suited for each specific token. If you ask a math question, only the mathematician part of the network activates. This allows models like the switch transformer to scale to over 1 trillion parameters while keeping the actual computation per token manageable. The second chapter is about the art of generation. LLMs are ultimately probabilistic machines. When a model predicts the next word, we don't always want it to pick the most likely one. That leads to repetitive robotic text. Instead, we use temperature to control creativity. A low temperature makes the model conservative and deterministic, great for facts, while a high temperature makes it creative and diverse, great for storytelling. We also explored guided decoding, which forces the model to follow specific rules, like ensuring an output is always in a valid JSON format. The final chapter focuses on the speed of thought through inference optimization. We looked at KV caching, which prevents the model from recalculating everything it has already read or written in a conversation. We also explored speculative decoding, a clever trick where a small, fast draft model quickly guesses a string of words and a large target model checks them all at once. If the big model agrees with the fast model, the generation speed skyrockets because the big model is only doing a single check instead of multiple slow predictions. From the reasoning power of chain of thought prompting to the hardware-level optimizations like paged attention, these techniques are what turn a basic transformer into a high-performance assistant.
The journey of an AI begins with pre-training. Think of this as the internet knowledge phase. Researchers take trillions of tokens, basically the entire internet, from Wikipedia and Reddit to massive piles of code and feed it to a model with one simple goal: predict the next word. By doing this, the model learns the structure of human language. However, these models have a knowledge cutoff. Because training is so expensive and takes months, a model finished today might be completely clueless about events that happened yesterday. Now, how do we actually power this process? It's all about GPUs. Because LLMs are essentially giant math problems, we need specialized hardware. But even the best chips have limited memory. To solve this, engineers use data parallelism, splitting the workload across thousands of GPUs so they can work in sync. There's also a brilliant trick developed at Stanford called flash attention. Instead of the model constantly reading and writing to the slow part of the GPU's memory, flash attention tiles the data into tiny pieces that stay in the chip's fast lane. This speeds up training significantly by cutting out the middleman. But after all that math, the model still isn't very helpful. If you ask a raw, pre-trained model, how do I wash a teddy bear? It might just start listing different species of bears because it's just trying to predict the next word. It doesn't know it's an assistant yet. This is where instruction tuning comes in. We take that base model and feed it a high-quality dataset of questions and answers. This aligns the model, teaching it to follow directions, be helpful, and follow safety rules. To make this step even cheaper, we use LoRa. Instead of retraining the whole model, we freeze the original brain and only train a tiny adapter on the side. It's the ultimate shortcut for turning a raw machine into a specialized assistant. If you've ever felt like modern AI models are a bit too robotic or unpredictable, you're not alone. The journey of an AI begins with pre-training, where the model learns the structure of language by reading trillions of words from the internet. But at this stage, the model is just a powerful autocompleter. If you ask it how to wash a teddy bear, it might just start listing different types of bears instead of giving you advice. To fix this, we move to supervised fine-tuning, or SFT. This is where we feed the model high-quality examples of questions and answers to teach it how to act like an assistant. While this makes the model more useful, it still might be too blunt or provide safe but unfriendly responses. This leads us to the heart of the lecture: preference tuning. This is the secret sauce that aligns the model with human values. Instead of just telling the model what to say, we show it two different responses to the same prompt. One winning response and one losing response, and ask it to learn which one humans prefer. One famous way to do this is RLHF, or reinforcement learning from human feedback. It involves building a reward model that acts like a judge, scoring the AI's answers. The AI then uses an algorithm called PPO to maximize its reward scores without straying too far from its original knowledge. It's a bit like training a puppy with treats, but on a massive computational scale. However, RLHF is notoriously difficult and expensive to run. That's why researchers developed DPO, or direct preference optimization. DPO skips the middleman of the judge model and directly updates the AI's weights based on the preference pairs. It's faster, more stable, and effectively treats the language model as its own reward system. Whether it's making an assistant sound gentler or ensuring its advice is safer, preference tuning is what transforms a raw machine into the polished AI we interact with every day.
Is a major milestone because we are moving beyond vanilla large language models. Think back to the standard pipeline. First is pre-training, where the model learns language and code by predicting the next token. Second is supervised fine-tuning, where it learns to behave like an assistant. Third is preference tuning, where reinforcement learning with human feedback aligns it with human values. Even after all this, there's still a major limitation. The model is a System 1 thinker. It predicts quickly, but it does not think before it speaks. This works well for writing or summarization, but it often fails at math and logic. To solve this, we define reasoning as solving non-trivial problems using multiple steps. For example, answering a direct question is simple, but calculating the age of something based on years requires understanding and step-by-step thinking. This leads to chain of thought. Instead of giving a final answer immediately, the model generates intermediate steps. By producing more tokens, the model gets more compute and breaks the problem into smaller parts it understands. You may have seen this as a thinking phase before the final answer. This is not just for display, it improves accuracy. However, prompting alone does not scale. We cannot manually create reasoning examples for everything, so we use reinforcement learning. Instead of telling the model how to think, we give it a goal. Reasoning tasks help because they are verifiable. In coding, the program either works or it does not. In math, the answer is either correct or wrong. The model generates multiple solutions and learns from which ones succeed. To measure this, we use benchmarks like human evil for coding and AEME for math. Since models are probabilistic, one attempt may fail, so we use pass at K. This measures the chance that at least one out of multiple attempts is correct. This is the shift to the reasoning era. Models are moving from generating text to solving problems step by step. Imagine an AI that knows everything up until last year, but has no idea what happened this morning. This is the knowledge cutoff, and it's the wall that every major language model eventually hits. Our journey begins with the realization that even the smartest models are effectively frozen in time once their training ends. You can't just keep retraining them every day. It's too expensive and risks making the AI forget its older core knowledge. So how do we give an AI fresh eyes? The first breakthrough is called RAG, or Retrieval Augmented Generation. Think of it like giving the AI an open book exam. Instead of relying on its memory, the system acts like a librarian. When you ask a question, it searches a massive knowledge base, pulls out only the most relevant chunks of information, and glues them directly into your prompt. This allows the model to answer questions about today's news or your private documents without ever being trained on them. But reading isn't enough. What if the AI needs to do something? This leads us to tool calling. This is where the AI stops being just a talker and starts being a doer. By defining specific functions, like checking the weather, calculating complex math in Python, or searching for a product, we give the AI a digital toolbox. If you ask for a teddy bear near me, the model doesn't just hallucinate an answer. It recognizes it needs a tool, triggers a function to find your GPS location, queries a stored database, and then translates that raw data back into a helpful response. The final, most exciting stage of this evolution is the agent. If RAG is the library and tools are the hammer, an agent is the carpenter. Using a framework called REACT, Reason plus Act, the AI doesn't just follow a single instruction. It enters a loop, it observes a problem, creates a plan, takes an action, and then checks the result to see if it worked. If you tell an agent, my teddy bear is cold, it observes the room temperature is 65 degrees, plans to fix it, calls the thermostat tool to raise the heat, and then verifies the room is warming up before telling you the job is done. But with great power comes the needle in a haystack problem. If you give an AI too many tools or too much information at once, it gets confused and misses the point. To solve this, researchers use tool selection or routers to narrow down the choices, and new standards like the Model Context Protocol to make sure different AIs can use the same tools safely. We are moving from AI that merely predicts the next word to AI that pursues goals autonomously. Ever wonder how engineers actually know if an AI is getting smarter or if it's just getting better at faking it? We're going to show you how we measure the soul of a language model, from its logic to its safety, and why most of the numbers you see online might actually be lying to you. Our story begins with the problem of the fuzzy mirror. Because AI can output anything from poetry to Python code, traditional grading doesn't work. If you ask a human to rate an AI's advice on a birthday gift, one person might call it sweet, while another calls it useless because it didn't specify exactly which brand of teddy bear to buy. To fix this, researchers use inter-rater agreement metrics to ensure humans aren't just guessing, but human grading is slow, expensive, and it doesn't scale. This led to the era of rule-based robots and metrics like Meteor and Blue. These systems compare AI answers to a perfect human reference. But there's a catch. They are rigid. If the AI says a plush toy instead of a stuffed animal, the robot gives it a 0, even though the meaning is identical. The real breakthrough came when researchers realized they could use the AI to police itself. This is LLM as a judge. By asking a more powerful model to explain its reasoning, a rationale, before giving a score, we get a grade we can actually trust. But even these digital judges have human flaws. They suffer from position bias, preferring whichever answer they read first, verbosity bias, favoring longer, wordier answers, and self-enhancement bias, where an AI secretly prefers its own writing style over competitors. To truly test an AI's mettle, we put it through the academic gauntlet, a series of benchmarks that act like the SATs for machines. MMLU tests its broad world knowledge across 60 subjects like law and medicine. Amy and PyQO push its logic, asking it to solve complex math or explain common-sense physical problems like why you'd use a hairnet to find a lost earring in a carpet. Then there's SWE Bench, which forces the AI to act like a software engineer, fixing real bugs on GitHub to prove it can actually build things, not just talk about them. But as we reach the frontier of AI agents, models that can browse the web or buy tickets for you, evaluation becomes a simulated life. Using frameworks like Tau Bench, we simulate a user and an agent in a loop to see if the AI can actually complete a task like changing a flight without breaking the database. The ultimate lesson? A high score on a test doesn't always mean a good model. When a measure becomes a target, it ceases to be a good measure. The only way to truly know if an AI is ready for the real world is to test its reasoning, its safety, and its ability to act. Imagine trying to teach a machine not just to read, but to see, to reason, and even to hallucinate with purpose. Our story begins with the secret sauce of modern AI, self-attention. For years, machines read text one word at a time, often forgetting the beginning of a sentence by the time they reached the end, but the transformer changed everything by allowing every word to look at every other word simultaneously. But why stop at words? Researchers soon realized that if you chop an image into tiny patches, the transformer could treat those patches like visual words. This gave birth to the vision transformer, proving that a machine could understand a picture of a teddy bear using the exact same logic it uses to understand a poem. The plot thickens with the arrival of digital reasoning. We used to just want AI to autocomplete our sentences, but now we want it to think. By using reinforcement learning, essentially giving the AI a reward for being helpful and a penalty for being wrong, we taught models to show their work. Instead of just jumping to an answer, they now generate a chain of thought, reasoning through a math problem just like a student would on a chalkboard. But even a thinking machine has limits. It only knows what it was taught during its schooling or pre-training. To solve this, we gave AI a library and a toolbox. Through retrieval augmented generation, or RAG, the AI can look up real-time information it wasn't trained on. And through tool calling, it can actually step out of its text box to run code or check a calendar. The final chapter of our story looks at the future, diffusion. While most AIs write one word at a time, new diffusion-based models are learning to create text all at once, starting with a cloud of noise and gradually refining it into a perfect sentence. It's a faster, more creative way to generate language that could make the AI of tomorrow 10 times quicker than what we have today. As we close the book on this lecture, remember that the goal isn't just to make models bigger, but to make them more efficient, more grounded, and more human-aligned.